The Johns Hopkins Science Review, presented by the Johns Hopkins University and WAAM in Baltimore. This is the Johns Hopkins University, famed for 75 years for its contributions to science and the humanities. Here in its many laboratories, Hopkins scientists are constantly probing into the basic, still unknown secrets of science, which, when discovered, are translated into benefits to be enjoyed by you, the people of America. Each week at this time, we catch a glimpse of the results of their research. Tonight, we ask the question, epidemic theory, what is it? To introduce tonight's demonstration, here is Lynn Poole of the Johns Hopkins University.
Good evening, ladies and gentlemen. It's always a pleasure on Tuesday nights to greet you people along the East Coast and out in Chicago and Cleveland and Columbus. We're very happy to announce tonight that 2 new cities have joined our network. It's a pleasure to salute these people and the stations in Rock Island and in Omaha. We're honored to greet the people in Omaha, Nebraska, and in Rock Island. Rock Island, we hope we're going to make many good friends tonight whom we will see for many Tuesday nights to come as they watch us over that pioneering television station, WHBF-TV. Rock Island, long a great railroad center, is also a center of agriculture and progressive industry. Well known for its cultural and educational development, WHBF-TV is a leader in its community. We also send our greetings to the residents of Moline, Illinois and Davenport, Iowa, who may be watching the program over WHBF-TV. We hope you'll be with us for many months to come. At the same time, it's our privilege to pay our sincere respects to the people of Omaha, Nebraska, where station KMTV is making it possible for us to come into your homes. Also a great railroad center, Omaha is the home of fine institutions such as Omaha University, Creighton University, and the Jocelyn Memorial Art Museum. We are proud to be associated with Omaha and station KMTV. At the same time, we send our greetings to those of you in Council Bluffs, Iowa, and Lincoln, Nebraska, who may be watching us from KMTV. The station KMTV and WHBF-TV, and to all you people in the Midwest, we want to tell you and pledge to you that we will work hard to bring you programs that are entertaining and programs that are worthwhile. And now to tonight's program. The word epidemic has struck terror into the hearts of many people for many centuries. Diseases have ravaged entire cities as they spread from person to person, and indeed they have ravaged entire countries. Epidemic is a word that people feared for a long time. But with the advent of modern medicine, the epidemic, scourge of disease passing from person to person, has almost been wiped out. This has been done by our medical scientists working in their laboratories day after day in our behalf. A theory has been developed about epidemics, a theory that applies to you and to me. That's the theory we want to demonstrate tonight. So it's my privilege to present our guest, a great public health servant, the Vice President of Johns Hopkins University and Hospital, Dr. Lowell J. Reed.
I'm going to talk to you this evening about epidemic theory and epidemiology. This subject is one that is comparatively recent and the terms are unknown to most people. The word epidemiology itself means upon the people and indicates that a disease has descended upon the people as a pestilence. Our theory and scientific work in this field is comparatively recent. But although the scientific work is recent, epidemics have been recognized from time immemorial. Primitive people saw disease descend upon them, and they thought that they had incurred the wrath of their gods. They gave a religious interpretation to the event. We find records of epidemics in the Bible. We see that epidemics have destroyed certain races of people. One striking instance of this was the big epidemic that occurred among the Indians in Massachusetts the year before the Pilgrims landed. Their landing was made possible by the fact that an epidemic had wiped out a major portion of the Indians of that region. And so epidemics have been observed by primitive peoples from the beginnings of time. but it's only recently that we've had the development of the theory. The possibilities of the theory arose when we knew the origin of disease, when bacteria were discovered, and we found that diseases were transmitted from person to person by transmitting these disease agents, the bacteria and the viruses. Then we had the beginnings of epidemic theory. We saw these epidemics in striking practice. Smallpox was particularly noticeable. In the early days, for instance, in Baltimore, when smallpox was not prevalent in the city, a ship would come to the port carrying a sailor who had had smallpox, and as he moved among the people of the city with his case of the disease, he transmitted that disease to some of the people of the city. Those individuals, in turn, transmitted the disease to other individuals. And before long, we had a full-spread epidemic of smallpox. This created the notion that the epidemic was a natural flow of the disease process through the people. And the epidemic theory attempts to study and explain this natural flow. We must not expect any epidemic theory to cover all diseases. Each disease will have its own epidemiology, some simple and some complex. Malaria, for instance, is one with a complex epidemiology. In this case, an individual who has malaria may be bitten by a malaria-carrying mosquito. That mosquito then picks up the disease and becomes an infected mosquito, a diseased mosquito. That mosquito, again, biting another individual, will transmit the disease to that other individual. And thus we have the disease moving from individual to mosquito back to individual. Malaria, again, has relapses of its cases, and this increases the complexity of the study of malaria. So each disease will vary in the degree of its complexity, but we may hope to understand the process if we can understand the flow, and may see how to develop the science of epidemiology for any particular disease.
Once the scientists realized the cause of diseases, realized the virus, the bacteria that was in the air, in our food, in our water, he could then develop somewhat of a theory about epidemics. But it's the nature of a scientist that when he has a problem, he must develop a theory that must be proven, and proven conclusively. So first, I'd like you to take a look at this epidemic theory that has been developed by the modern scientist.
The work on epidemic theory in a mathematical sense is over 100 years old. William Farr, the great epidemiologist in England, developed a mathematical equation to express the epidemiology of smallpox and applied it to one of the great epidemics of smallpox in Great Britain. 25 years later, he applied this theory again to an epidemic of cattle plague that threatened to destroy all of the cattle of Great Britain. His work on the cattle plague was so dramatic that it was reported in the House of Commons and had its effect in the measures that were taken to control the cattle plague. Work of this sort was carried on by other men following Farr, and we have mathematical expression for the epidemiology of several diseases. I shall not attempt to go into the complex cases this evening, but shall take up the simple case that is represented by measles. The case where the disease is transmitted from the sick person to a susceptible person, and from a susceptible, the susceptible person then taking the disease and becoming ill. We call that a simple person-to-person transfer of the disease with no intermediate agent. We may represent that process in a population city as follows. The people in our city will be made up of various types. One type will be the susceptible people. Those are the people who have not had the disease and are capable of taking the disease if they encounter a case. And so the cases are the other people in the city that make the epidemic possible. It is the cases meeting the susceptibles and giving them the disease that give rise to the new cases. And so any mathematical equation will have to express the flow of the disease from cases to susceptibles to new cases. The mathematical equation that's been developed for this particular case is represented as follows. The cases in the subsequent time period, which might be 2 weeks later than the initial start of the epidemic, is equal to the susceptibles at the time period multiplied by a factor which is the probability that those susceptibles will meet some one of these cases, C sub t. So the equation C sub t plus 1 equals ST times 1 minus q to the CT power is the mathematical equation for the epidemic. That seems complex, but is more simple than it looks. We might symbolize that by diagramming some of the people involved. Here is an individual that would represent one of the susceptibles, an individual in flight because he is hoping to escape from this individual who is the case. And so here we have the case of the disease pursuing the susceptible. If the case does meet the susceptible, then that susceptible will become a new case and will be taken ill and have the disease himself. That's the fundamentals of the process. The epidemic flow would be represented by a situation of this sort. A group of susceptibles in the population who are individuals who have not had the disease and may acquire the disease if they meet a case, and a case introduced into that group of susceptibles. If the case here meets one of the susceptibles, for instance this one, then that individual becomes ill and he becomes a new case. If that case meets another susceptible, then that susceptible becomes ill. And we might say that that case has given rise to 2 new cases. That would be called an epidemiological rate of 2, 1 case giving rise to 2. The next stage of the process would occur with measles approximately 2 weeks later, when this case had recovered, and he then goes into another class of people, the immune, the people who have had the disease and are no longer in danger of having the disease. And so in the next stage of the disease, this case becomes an immune, the person who is happy to be through with the process. He's had his case and is through. However, he's passed it on to these 2 cases, and those 2 cases are now the cases that continue the epidemic process. They are the cases that are circulating in the population and may have contact with the susceptible. If they in turn meet this susceptible, that susceptible will come down as a case. If they meet this susceptible, that susceptible will come down as a case. And so we'll have the susceptibles constantly moving into the category of new cases as they encounter the old cases. These old cases then would become the immunes, and we have the natural flow then of the disease into the susceptible flowing to the new cases, and the cases as they recover flow into the immune. That represents then the flow of the disease in the population, the thing that we are studying and the thing that is represented by this epidemic equation.
Well, this epidemic equation may have seemed most complex and most difficult to us when we first saw it a moment ago. But with Dr. Reed's explanation of his happy people and his unhappy people, his cases, his susceptibles, becoming immune cases, it becomes very easy to see what the equation means. Now, this mathematical equation is an epidemic theory. But before any scientist, any good scientist, will accept a theory, accept a mathematical equation, that theory must be proved. It must be proved conclusively. So it's taken into the laboratory. And in some way, a method is evolved to prove that theory. Because if it's not right, someone else will disprove it. This theory that Dr. Reed has just been showing you was taken into the laboratory, and it was proved. And Dr. Reed has a very simple piece of apparatus here to show us how this equation, how this epidemic theory was proved in the laboratory.
Mathematical equations, such as the one you've just seen, need to be tested against experience. This one has been tried against a number of epidemics of measles in actual fact, epidemics of measles in several of the big cities in the world. The agreement between the observed cases of the epidemic and the theory is very good. However, to test this equation against observed epidemics is a slow process because epidemics occur only occasionally, and our records of these epidemics are not as good as we might wish. We therefore want some simple mechanism by which we can test the principles involved in this theory within the laboratory. For this purpose, we've designed a very simple machine that will allow us to consider the theory and apply it within the laboratory. We have here a wooden trough, which may be thought of as the city within which the people will live and move and circulate. That then is the city for a group of people that will be represented by simple beads. These white beads are susceptible individuals. They are the people who have not had the disease and may acquire the disease. The other class of people of interest is naturally the cases. These spotted beads represent the cases. They are the people who are ill. It is those individuals that will transfer the disease to these susceptible individuals. When the individual has had his case and is recovered, he then becomes an immune person, which will be represented by the purple beads. So that we'll have the three categories of people that are essential to a simple epidemic: the susceptibles, the cases, and the immune. We're now ready to try a simple epidemic with this machine. We may start an epidemic by assuming that we have 100 susceptible people. We'll put those 100 people together. We will introduce into that population one case. We'll have here a case of measles that we'll put in with that population. We must have some procedure for allowing chance contact to play, allowing that case to come into contact with the others. We shall accomplish that by making use of these slack beads, which are barriers, and you will see the effect of those as the epidemic is run. Now, to operate an epidemic, we have here 100 susceptible people. We have a case. They now start their process of living and moving within the city and mixing together according to chance. And in that chance mixing, that case will meet a certain number of susceptibles and will produce new cases. And we shall see the result of the epidemic. Here we have the epidemic with one case here, and it is in contact with 4 susceptibles. In contact with 4 susceptibles because it falls between the black balls. So that this one case, in circulating through the city, has encountered 4 susceptible people. The next step of the epidemic, of course, means that this case here now recovers from his disease, and he becomes an immune. And so we introduce an immune. This susceptible person that was in contact with him now becomes a case. And so with the other susceptible people. And so we replace these 3 susceptible people with 3 cases. We have a total of 4 susceptibles, have 4 cases now. Our population then stands. Our original case is an immune, and we have 4 new cases. Therefore, we have a remainder of 95 susceptibles. That would represent the first stage of the epidemic and the first transfer from the case to the susceptible. The next stage of transfer would be the events that would follow from having 4 cases now circulating in the population. And we can see the 4 cases circulating the population, producing disease according to the individuals with whom they come in contact. Here we have our 4 cases. This one here has encountered 1 susceptible. Therefore, he's produced one case. This case has encountered one susceptible. Therefore, has produced one case. This case here has encountered 5 susceptibles. Therefore, he's produced 5 cases. This one has encountered 1 and has produced 1. So that our 4 cases have produced 1, 5, or 6, 7, 8 cases. And we can pass to the next stage of our epidemic by removing the 4 cases, since they are now cured, and putting in 4 immunes. We will remove the 8 susceptibles that acquired the disease in this and put in 8 cases. Thus, our population, a group of people, now stands as a population with 5 immunes in it, and with 8 cases, and with 87 susceptible people. The next stage of the epidemic will come from the movement of those 8 cases in that population. And we see that this case has met with 4 susceptibles, this with 3, that's 7 new cases, this with none, this with none, this with 5, that makes 12 new cases, this with 2, that's 14, this with 5 more, 19, 1 more is 20. So those 8 cases produce 20. So that our epidemic, starting with 1 case, that case transferred it to 4, the 4 transferred it to 8, the 8 transferred the disease to 20 people. We will find that as we continue this process, that the epidemic will die out eventually. The reason for its dying out is that the susceptibles will be used up. We will have burned away the fuel on which the epidemic lives, and so the epidemic will come to a natural stop. We will find also that we'll not use all of those susceptibles in the process. It will only be a part of the susceptibles that will be used up before the epidemic will stop in its natural course. That shows you
In this way, the scientist proves in his laboratory a theory that has been mathematically worked out. The scientist working in his laboratory is not working in a nebulous cloud. He's working for something. He's working for you, and he's working for me. And I think we'd like to know what the practical result of the proof of this laboratory theory can do for us.
In developing any theory, such as the one you've just seen, we naturally have in mind its possible application. What we wish to do with epidemics, of course, is control them. It's the object of the health officer and the doctor to exert this control. We hope to learn, through this study of the epidemic theory, which methods of control are most effective. There are numerous methods that have been used to control or stop epidemics. 2 of the most common methods are represented by, first, the isolation of the case. In this method of control, the attempt is made to pick up the case sufficiently early in the stage of the disease so that we can separate it from the susceptible and therefore not give rise to new cases. We build our isolation hospitals for this purpose of control. The second method of control is that of the immunization of the susceptible. In this process, we desire to transfer people from the susceptible class to the immune class without their going through the disease process. This can be done if we can develop a process by which we can immunize people. Immunizing processes are simple biological procedures by which a person acquires that biological state that presents his becoming ill. If we can immunize a sufficient number of the population, we'll find that the epidemic will die out naturally. Or with a given proportion immunized, a case introduced into the population will not start an epidemic. Our hope therefore in our immunization procedures is to have a sufficient number of the people immunized so that no epidemic will start if we introduce the person. This machine and this theory can be used to test ideas of this sort. I've illustrated a few of those, but we would apply the theory to many other epidemic concepts.
This is another example how the scientist working in his laboratory is working for you and working for me, all of us together. The epidemic theories that you've seen demonstrated here tonight apply to us. They come down to us through the public health officer, through our own doctors in all of our cities. Again, we'd like to welcome the people out in Rock Island and out in Omaha, Nebraska. We're awfully glad to have you with us. We hope that we can come into your homes often. We also hope that you'll be with us next week when the Johns Hopkins Science Review on Tuesday night gets a glimpse of troubled people meet.
When we think of psychiatric treatment, we usually think of a doctor treating one patient in the privacy of his office. However, psychiatrists have learned that certain types of patients can be more successfully treated in groups. Those who suffer from psychoneurosis can often aid each other by sitting together with a psychiatrist and discussing their mutual problems. Next week, Dr. Jerome Franks will conduct a group therapy meeting and allow us to watch, to learn how such treatment is carried out. Be with us next week when we watch as troubled people meet. Johns Hopkins Science Review was written by Lynn Poole. Produced and directed by Anthony Farrar for WAAF. Associate producer, Sterling Reynolds. Settings by Barry Mansfield. The announcer was Joel Chase. Johns Hopkins Science Review originated in the studios of WAAM in Boston. This is the Dumont Television Network. It's the freshest fish you can find. Chicken of the